And here we are. This is the end. The end times are upon us. It's been a fun ride, but let's go ahead and see this through to the end, because we have just a little bit left to say on parametric equations, and then we will have seen all of it. Except for, I guess, some of the bonus content that we'll get to after this, but this is the last of the material that you really have to do anything with in this course. And that thing that we're dealing with is parametric equations, and it is not parametric functions. A parametric function is not a function. That's what I want us to start off with here. It's not quite correct to call a parametric equation a function. And that is because a function has a single output traditionally. It's going to have one output for input. Or even you can have a function in two variables, which you'll get to pretty deep in your math experience, where you start having equations in more than one variable. So for a function in two variables, you have two different inputs. Three variables, you have three different inputs, and so on. And what happens there is for every unique set of inputs, you have exactly one output. And so what this might look like, and I'm not going to be able to sketch this out for you, this is a three-dimensional plane curve. This says that for whatever x and y you put in here, you square and you add together, that tells you your height, that tells you your z-coordinate. And that makes a curve. And there's only one output z for every single ordered pair you put in. And we will not worry about three-dimensional surfaces in this course. We will not worry about it in Calculus 1, and we pretty much won't worry about it in Calculus 2 either. It's a Calc 3 on kind of topic, because it's that complicated. Not difficult, just complicated. Right? Just because something is simple doesn't mean it's easy, and conversely, just because something is complicated does not mean it's hard. It's a very complicated topic, and we do put it off until pretty deep in the experience there. But yeah, it is not a function. It's not a function. It's more accurate, it's more correct to say that a parametric equation is a pair of functions, because that is correct. Because you get your x and your y, those two variables, in terms of a parameter t. And so t would be your independent variable, and x and y each respectively depend on t. So you'd have a pair of functions. And that together makes your parametric equation. And that makes your plane curve with your direction. Just something to hold on to. Now, I want to go ahead and say this, because we've seen it in class a little bit, we've talked about it, we've asked some questions about this. When should I or shouldn't I eliminate the parameter? And I'll go ahead and give you the realist advice I can, and that is, well, if it's a simple enough equation that you can eliminate the parameter, chances are good that it doesn't really matter. You could probably see it through to the end without having done so. Conversely, if it's such a complicated curve that you have to eliminate the parameter, well, chances are good that you couldn't even if you wanted to. For instance, to kind of seal the deal on this, I have researched, looked up, and made a graph of hypotrochoid curves, which is a delight to say. And the way it works is you pick, I think it's 3 different constants. So you just pick 3 different numbers, A, B, and H, and you take those things and you use those as constants, so you pick those in advance. And that makes your x function there, because that depends exclusively on t now, because the other things are fixed. And then you make your y function accordingly. So you just switch your cosines for your sines. And the end result is nothing short of beautiful. That right there is a hypotrochoid. The constants I have picked in advance is 5, 5, and 3. I had to kind of move some of the placeholders around because Desmos is rather finicky with some of the letters you choose. Gets a little upset sometimes. But all the same, this is a hypotrochoid curve. It's a star. And I wish you the best of luck. I wish you all the luck in the world finding some rectangular equation or even finding some polar equation or function that generates this star. Just go ahead, go crazy, go nuts. Go find some. And so hopefully this seals the deal. This clinches it that yes, you do need some graphing tool to handle these complicated things. Also, you see my point moving around? This shows you the direction that my parametric curve is being traced out. But what if I had some other constant? 6. Or what about 7? Or 8? Or 2? Or 3? Or 0.5? Hypotrochoids are incredibly diverse things. They can do a lot, and it really just depends on the constants. I mean, it's got a star pattern going on, right? Well, let's just say it's got a star pattern when this number is equal to 5. What if it's 6? What if it's 7? What if it's 8? That's pretty. And there was this guy too. What if that's 5? What if that's 6? That's pretty. These are all curves made by this same set of equations, just for different constants. And yeah, go ahead, go nuts. Go find some rectangular equation that makes this curve. I just don't advise it, really. I was being a little sarcastic there. So don't actually do it. Anyway, just so you know, these curves are actually being traced out by putting a wheel inside of another wheel and having the center of that smaller wheel an arm that's spinning as the smaller wheel rotates inside of the larger wheel. Hang on, let me show you what that means. There we go. Borrowed by Wolfram Alpha, right? This is an animated illustration of what hypotrochoids look like when they're traced out. So you have some smaller wheel rotating inside a larger wheel. And in that smaller wheel, on an arm of whatever length, it can be even sticking outside of the big wheel, you're tracing out a path. And so it all depends on several variables, right? What's this length h? What's this radius b? And what's this larger radius a? And depending on what constants you choose, you can make very pretty and very crazy graphs. Very crazy indeed. Alright, well, that's enough of that. You're like, oh, this is too impractical. Okay, fine. Let's do just one more thing here. Just kind of have a little bit of fun for you in our time together. I want us to do one last one. And I want you to take a second to kind of trace this out yourself. I want to see what the plane curve made from the parametric equations of x equal cosine t looks like, and y sine t. So all that together, give me a parametric graph. And go ahead and do a little bit of that on your own. And I'll kind of work alongside you here. Because I know at t equals 0, we've got cosine of 0, sine of 0. So 1 comma 0. At pi over 6, I'm at x equaling root 3 over 2, which is about 0.7. And y is about 1/2. Then at pi over 4, I'm at root 2 over 2 comma root 2 over 2. That's about that's about 0.7 comma 0.7, sorry. So that's about there. And then we're looking at 1/2 comma root 3 over 2, followed by 0 comma 1. And in fact, if you just keep going like this, I'll leave that out, you'll eventually end up at the curve cosine t comma sine t. And this is going to go from, however far we need to get it to go. Oh, wait a minute. This is the unit circle. Right, the parametric graph generated by having x be given by cosine t, y be given by sine t is the unit circle. But wait again. I think that's how we defined cosine and sine from the very beginning on the unit circle approach. In fact, if you were to look back to the beginning of your notes, the very, very beginning, one of the very first things we looked at was we actually defined x to be cosine t, y to be sine of t, and we asked the question, and you look, check it out. We asked the question, is that parametric? And finally, we can finally say, yes. Yes, it is. The unit circle, and trigonometry as we know it, was defined out as being a parametric equation. So I guess that means we have come full circle. And as you groan and moan at that awful pun, I bring you this. This is our last slide. We have reached the end of the content, and you have made it all the way here. That's it. There's just one other kind of neat application that we'll look at, such as we have time, but this is it. We've done it. So, I hope this has been a good time for you. I hope that this approach has been beneficial for you. I hope that you've gotten more out of this than you would have gotten with just me standing and rattling off the same stuff for hours at a time. I hope this has been good. And we will get comments back from you in person. Right now, when it comes to evaluations, I'll hear back from you. And I want to hear back from you. I want to know how this worked. What went well, what went poorly, what could be different, what could be kept the same, what could be improved on, what could be left behind, all that. Because we are at the end of the semester. We are at the end of the course. So the time has come not to continue learning new things, but to look back, put together all the stuff we've looked at, all the stuff we've learned, and see how we fare. So it's been a real privilege and an honor taking you out here, coming out with me. It's been a real treat. So thank you, and have a good one, and best of luck in all your future endeavors.